So in this video, we're going to talk about friction, types of friction. And there's four real types of friction. There's static friction, symbolized with an F and a subscript S, kinetic friction, rolling friction, fluid friction, and there's the symbol for each one of them that usually represents it. It might be slightly different depending on who writes it, but this is the basic premise. Now, we're mostly going to focus on these three right here, because static, kinetic, and rolling all have to do with solid surfaces touching one another. This last one, fluid friction, ends up being a little bit different because of how it's dealing with, well, fluids, really. And so the calculations are a little bit different and things like that, but we still want to understand some conceptual things with it while we're getting to know even a mathematical relationship with these three that deal with solid surfaces. Now, first up, we have static friction. Static, if you're not familiar, just means standing still. It's not moving. Now, if you think about static friction, the way I always think about it is it's basically Newton's first law, that object's ability to resist moving, right? But it has to do when two solids are sitting on top of each other. It's most easily seen if you've ever tried to push something really heavy, like, say, a refrigerator. Here's my refrigerator, and here's me trying to push it. And I would push it across this floor, and I would start to push, and I would push and push and push and push, but it doesn't really want to move. However, once I got it moving, it seemed to be easier to push. Well, all of this has to do with if you could look at that surface where those two solids connect, where the refrigerator and the floor touch, you would see that the floor is not really that solid or that smooth, neither is the refrigerator. In fact, the floor probably looks something quite jagged like that. And so does the bottom of the refrigerator. In fact, they might interlock in certain places. And because of that, it obviously doesn't want to move in the direction you're pushing it to the side. In fact, all of those rough edges are bumping into each other, and that's what's causing that static friction. It doesn't want to start to even move. Now, with kinetic friction, it already has started moving. But in this case, we're going to look down here, and you would see that it's now slightly above each other. So because you have the rough ends, but you've started to move, they're not going to be as deep set anymore. So it's less of it running into each other, meaning it's going to move a little bit easier, because kinetic friction means that it's already moving. And so static friction is where it's locked in place. Those rough edges are pretty much sunk into each other. Kinetic friction, you still have rough edges that are bumping into each other, but they're not as deep set as static friction, so it's a little bit easier. And then, of course, rolling friction. Well, rolling friction works way better than the other two, because now you have something where it's sitting on wheels. So if I'm looking at it with rolling friction, yes, I have my rough surface of that, and technically a wheel that I would have on it, and I'm going to make my wheel red up here now. Let's say that I put a wheel on the bottom of this. These wheels would have semi-rough surfaces too, but they're rounded, meaning it's going to just roll on top of it, so we'll be putting in the grooves and out of the groove, and so it's going to have even less friction than the kinetic friction. And so they do go in that order, and that's one of the first things that we need to understand, is that, truthfully, your largest friction is going to be static friction. It's going to be greater than kinetic friction, which would be next, which is greater than rolling friction. Now, with fluid friction, often the time it's used in order to even lubricate wheels and ball bearings. Therefore, it's often considered to be less than rolling friction. However, because of the way you calculate a fluid friction, we'll find out that might not always be true. Okay, so that's why we're primarily looking at just these three, because that statement is very true. it's only sometimes true that the fluid friction or the drag friction is less than rolling friction. Now we need to understand that with friction, for solid surfaces, it's pretty easy to calculate, because anytime you have a solid surface and an object sitting on it, we know that you're going to have gravity pulling down and a normal force, as we learned in the last one, going up. Well, if you think about it, that's that connection that's going to cause those grooves to sit in each other. And so if we're figuring out friction, it's directly related to that force, specifically this normal force. And so if I'm calculating friction, all that I'm really going to be doing is I'm going to be multiplying the normal force times what we call the coefficient of friction. Now, it's a Greek letter that we call a mu. It looks like a fancy U to me, but it's a Greek letter called a mu, and it's just the coefficient of friction. So let's see if I can write that somewhere. That's the coefficient of friction. Now, of course, depending on the type of motion, you get different types of subscript. If this is kinetic motion, this is the kinetic coefficient of friction. But then again, if it is static, then it gets the S, and it's the static one. Now, this mu is different for every type of surface you could get. So it's a constant between two surfaces, because you can kind of calculate based on what type of surface, how porous it is, things like that. Most of the time that will have to have been scientifically and laboratorily tested in order to give you an idea. It's something that we would look up a lot of times. We can calculate it if we can figure out these two, though, the normal force and the frictional force already acting on it. And that's how it's calculated most of the time anyway. Any object could have a different coefficient of friction, but once you find out what that is, it usually stays as long as the object stays intact. So our formula for static friction would just be, here's static friction, it's going to be my normal force times that mu of static. Kinetic friction, normal force times mu of the kinetic. Rolling, well, that's a force. Needs to be an R. Normal force times the mu of rolling. And yes, my mu is pretty ugly for that one. But not for fluid. Fluid is the one that I said is more difficult because it has to do with a whole lot of different things. I'm going to show it to you right now. Just don't get too spooked out by it, because it's not something you have to memorize or use. But I just want to show you why it's so much more complicated. So if I'm coming up with drag, right, there's a lot of things I need to consider. And so it usually has to do with the amount of gravity pulling down or what it's being pushed through with water. And so a lot of times we say that the formula for it is negative 1/2 capital C, kind of a P looking thing, an A and a V squared. Okay, now this is very complicated because you need to know what each part of these things are, and they're harder to calculate. Our C here actually is its coefficient, kind of like the mu was, all right? It can range, though, from 0.5 to, which it is for a spherical object, to possibly 2, depending on how odd of a shape it has. And so this is calculated based on what it looks like. Spheres tend to move through things the easiest. So a spherical object, it's a little bit easier to calculate. It's 0.5. Now, the A over here is the cross section of the area. So it depends on how big the object is, how much air or water or whatever fluid it's hitting is going to interact with. So that's why the area would be important. The P is the density of the fluid that it's moving through. So if it's air, it's how dense is the air. Like upper atmosphere is less dense than lower atmosphere. Certain gases, if you're in a certain gas, can be more dense than another one. V is a velocity But notice it has to be squared as well. So it depends on how fast it's going, really, in all of this as well. And so all of that has to be taken into consideration. And the shape of the object determines two key parts of it. The shape and size and area, really, cover how much it's going to cost. So it's a lot more complicated, and we don't actually have to do it. So I'm going to go ahead and tell you, you don't have to memorize this. All right, but you do need to get those down. All right, and that should do it for friction.